Welcome to week 2 of Advanced Hydronic Training. My name is Jim DePalma. Joining me today live in our studio here is John Resso. He'll be manning the question. Also remotely will be Rick Coster, also looking at questions. Sitting in the hot seat today is Christiane Levine, our Senior Marketing Manager, and she is running the program. So I wish you guys could see what we have cooking here. We have 3 people live, people in the background remotely. So we're putting in a lot of effort to do these classes. And we absolutely enjoy doing this. This is a lot of fun. So first things first, make sure you have all of your downloads available. Today, we are going to be doing system design. We are going to be doing math. And to get the most out of today's class, you're going to need your paperwork in front of you, or at least be able to access it via your computer. Have your smartphone calculator, or have a calculator on the side, pen, paper, so you could do some of these. So you could, I guess you can see the ring lights of my glasses. So you could do some of the calculations that we're asking you to do today. That's how you get the most out of it. When we do this class live, you know, I could get to see the reactions of the attendees that are there. And one of the things we tell them all the time is, if we do something today that you didn't understand, please ask and we'll do it again. All right? Because today we're going to go into system design. We're going to figure out how and why we do heat losses, and we'll do a heat loss for a room. So I really need you to be involved. So if there at any time, if we've covered something and you're not understanding, please go to your screen, the panel on the right hand side of your screen where it says questions, and please type in your question. And I'm more than happy that if you type in, please do that again. We'll do it as many times as necessary, because we want you to leave here today with really good information and understanding what we're doing, because we're going to build on this when we get into week 3 and week 4. The other thing for some more housekeeping is on your screen. Now I'm looking at a screen to my right, which shows me what you guys see. And you'll see on the top of your screen where it says webcams, and there's a down arrow. If you click on that down arrow and click left, now you should have a split screen, and I'm on the left-hand side of your screen, and you'll see the presentation on the right-hand side of your screen. You can find those 3 black little hash marks in between my view and the PowerPoint, and you can expand the PowerPoint or expand me, whatever you choose to do. So you can view this in a way that makes you guys comfortable. All right? Okay. We look good, Chris? Everything looking all right? All right. All right. So first things first, as we start every session after session 1, do you have questions from last week? We did have some technical difficulties, so you may have missed something as we were running around trying to get that up and running. But any questions you have from last week, please type them in and we'll answer them. Anything coming through, John? Nothing coming through? All right, so we're going to get going. So here's our agenda for today. We're going to go through system design. We're going to take you through how and why we do a heat loss. And if you're not doing heat losses now, this is a great day to be here, because you'll understand what it's about. I don't want you to get bogged down with the math that we're going to show you, because I want you to realize that we have plenty of software programs out there that do this math. But one of the reasons why we're going to do the math today is so you understand the information that you would be putting into, say, a RightSoft or a Uponor LoopCAD program, or the Takeo Hydronic Design program, which you can still download for free through the Takeo website. You do need to understand what the information is, and all these software programs are just calculators. So when it spits back some numbers, if the numbers don't look right, you have to understand that maybe you didn't give the right information. We're going to then go through typical heat load distribution. So normally when we do this class, we're sponsored by a wholesaler, so we're going to have at least a cast iron boiler option and a condensing boiler option. And we'll have the option of baseboard that wholesaler is currently offering, and maybe a panel rad and a radiant offering. So since we're not being sponsored by a wholesaler today, we're going to go with a condensing boiler, we're going to go with baseboard, and we'll do a radiant option also. So We've made those choices for you today. We'll also cover how to size the circulator, what information you need, all right, how to size the circulator, how to read a pump curve, and how to understand what a system curve is. So when we build our systems, even if it's the same square footage house as we did last week, and even the same BTUs, the two systems will still have two distinct system curves. And we'll make sure everybody understands what that is. And then last but not least, we'll go over a section of what is the difference between cast iron and condensing? How do we really make a condensing boiler condense? It says so on the box, right, John? It says 90, 95% on the box. So as soon as I pipe it up, plug it in, that's what we should get. And that's not really correct. We have to set up our system to make that boiler condense. And then can we still use cast iron boilers? Can we make them better? Are they still viable? And the answer is yes. So even if I'm doing an addition on somebody's home and I have a relatively young cast iron boiler, say 10, 15 years old, we could still use that and we can offer them more efficiency with new products that we have today. So that being said, off we go. So first item you're going to need from your download is the TACO training takeaways. And this is going to explain how we're doing a heat loss. And we're going to go step by step. So make sure you have TACO training takeaways in front of you so you can understand what we're talking about. So when we're going to do a heat loss, the first thing we have to do is do the first formula on the top. IDT minus ODT equals DDT. So what the heck does all that mean? So IDT is our indoor design temperature. What do you want to maintain in this building? Do you want to maintain 70? Do you want to maintain 72? Do you want to maintain 75? Do you want to maintain 68? Really depends on what the homeowner wants. Think about how you live in your own house, what type of temperature that you use to feel comfortable. So for today, we're going to use 70. So our goal today is to maintain 70 degrees in our floor plan that we're going to be using today. The next is ODT, outdoor design temperature. Now here's where I expect pushback. I need you guys to type in what do you use or what do you think you should use for your coldest day of the year in the territory that you work. What should be my coldest day of the year so I can design my system based around that? So if you wouldn't mind, just take a moment, type in, go to your questions and type in what we should be designing to. Are we designing to 0? Are we designing to a negative number? Tell me what you think we should design at. Give it a second or two.
Okay, I know a few of these names coming in, Jim. So for New Jersey, central New Jersey area, they're saying 14 degrees. I got one up in the Hudson Valley at 4 degrees. I see a minus 10. I don't know where Pete's from, but that's pretty cold. I see 15 degrees. I see 34 degrees.
Excellent.
0 degrees.
Excellent. Okay, there's a lot of really good answers in there. So let me explain why I asked that question. All the heat loss programs are going to use what's called an ASHRAE standard. And even if I was sitting here in New Jersey doing a design for Wisconsin, I can go into that program, find that area, Wisconsin, or whichever is the closest, and it'll tell me what the average coldest day of the year is in that area. So I live in northern New Jersey. I live in Passaic County. I'm a 20-minute bike ride to the New York State border, and with COVID traffic, I'm a 25-minute ride now to the GW or the Lincoln Tunnel. And right where I live, the average coldest day of the year is 14 degrees. We're coming to you today live out of Warren, New Jersey, and the ASHRAE standard average coldest day of the year is 14 degrees. If we go down to Atlantic City area, average coldest day of the year average is 15 degrees. We cross that great divide, this big ocean called the Hudson River, and get over into Manhattan or Long Island. Average coldest day of the year is 15 degrees. Now we get into lower Hudson Valley, then we're starting to get maybe into that 10-degree range. John is here with me today. He's way up in Kingston, New York area. What's your average coldest up there? 0. So as we go further north, it's going to get colder and colder. Northwest corner of New Jersey, we probably go with 10, maybe 5. All right. So it's really important that you know where the project's going to be so you can get that number. If you automatically go to 0 degrees, you'll be dramatically oversizing your equipment. So if your territory requires it, that's what you use. If it requires a negative number, that's what you use. So we're going to use 14 for today. So we're going to plug 14 into ODT. And when I subtract that from the IDT, that will give me my DTD, not easy to say. That will be my design temperature difference. So 70 minus 14 will give us 56. So that's going to be our DTD for today for this project. Any questions so far on how we got to that number? It's in the TACO training takeaways. So if you haven't found that information, make sure you got your TACO training takeaways in front of you. That was an attachment. So no questions? All right. So next we're going to do is we have to figure out what the infiltration factors are for every single room. We have to replace BTUs that we're going to lose on cold days because heat's going to go to cold. We have to replace the BTUs that are going to be leaving the building. So we're going to use a 10 by 15 room as an example for today. We're going to use a 10 by 15 room with 8-foot ceiling, and I have to decide how many outside walls that particular room has. So for today's example, I'm going to use 2 openings, 2 walls with 2 openings. So we're going to use 0.018 as the infiltration factor. So I'm going to put in the length times the width times the height times the DDT times the infiltration factor. So that would be 10 times 15 times 8 times 56 times 0.018. So plug those numbers in, do the math, and if you do the math, you should get 1,209.6 BTUs. So write that down because that's just one part of the equation so far. So one more time, length times width, 10 times 15 times height, 8 times 56, design temperature difference, times 0.018, 2 exposures, and that'll equal 1,209.6 BTUs. All right. Next, we have to now look at those exposed walls and find out how much square footage of glass is on there, and if we have also some doors. Okay. It's very interesting, especially when you walk on new construction sites and contractor will tell me, you know, they're going to spray foam this. It's going to be really super tight. And we look at a wall, could be a 15-foot wall, and I've got glass almost from floor to ceiling. Maybe I got a 3-foot knee wall. And he goes, yeah, they're going to spray foam all that in there. But in between all the glass is framing. It's wood. They can't spray foam in between. And the glass, unless it's really a high U value, it's still around an R2. And it's a wall of glass. So things like this, we do have to be very cognizant of. We have to pay attention to it. And you'll learn by just, you know, paying attention to this. You walk into a room, see a wall of glass like that, and you know that you're going to have a difficult time heating it. You may need a couple of heat sources to make that room comfortable. So I got to figure out how much glass is in this room. So for example, I'm going to use 2 windows, standard egress windows. Today in our construction is 3 by 5. So we're going to put in the square foot area of those windows. If you double up the width, it's 6 by 5, that's 30. So that 30 times your design temperature difference, 56, times U value. What's a U value? Well, these programs use U values. And as you can see on your paperwork, to get a U value, we're going to take 1 and divide it by R. So if I take 1 and divide it by an R value of 2, which would be your standard R value, I would get a 0.5 U value. All right. So if we plug that in and we do, let me see, 6 times 5 times 56 times 0.5, I should get 840 BTUs. That's what we're going to lose through the glass. Yes, sir.
Jim, suggestion here on the questions from someone. They asked if you could just go through it again a little slower and possibly maybe write the numbers down on the board.
Okay.
Just so they can follow you one more time.
Sure. Sure. So for the windows, or go back from infiltration?
I'd probably start, I got a question just like a minute ago, so I would probably start, just review it one more time.
Okay, not a problem. Happy to do it. All right. So for infiltration, we were doing a 10 by 15 room. Hopefully you guys can see that. So 10 by 15, 8's the ceiling height. 56 is that design temperature difference times 0.018. That was the exposures for 2 walls. That gives me 1209.6 BTU. All right, hopefully everybody can see that clearly. All right, so since the windows, we had 2 windows. 2 windows at 3 by 5, so I can combine the width to make it 6. So 6 by 5 times 56 again, which is the design temperature difference, times 0.5, which is the U value. And again, how did I get the U value? It was 1 divided by R, and it was 1 divided by 2 equal 0.5. I don't know if you can see that. I wrote it over to the side. All right. That's how we got that number. We do that math, and you should get 840 BTUs. I'll just stay here to do the walls. Walls will be next. Now, again, we have to find out what the U value is for the walls. So let's talk about wall construction. If this was new construction, standard construction methods now is a 2 by 6 wall. 2 by 6, our value is generally 19. Okay. If they tell you they're going to spray foam, maybe 1 inch and add some insulation on top of that, we can get up to an R25 or higher wall. Okay. If you're not 100% sure what the R values are, because new plans that we get don't normally tell us, look at the framing. If you see 2 by 6, minimum should be R19. If you're doing a renovation work and you're seeing 2 by 4 construction, well, you're starting off at either R11, maybe a 15. But if you're not sure, you got to poke around. You got to go look. You got to ask. All right. If you guys send us plans, which I get almost daily to help with radiant designs for contractors, I'm always asking questions. If I cannot find the insulation marked on the plan, or if I don't get a framing plan, I'm calling that contractor and he's going to have to give me that information. So if we do R19, to get the U value, we're going to take 1 and divide that by 19. That'll give me a 0.053 U value. So walls, 10 times 15 times 8, and I'm going to subtract the windows. We're taking that out, times my design temperature difference of 56, times 0.053. That'll give me 3,472.56 BTU. And we're not done yet. We got one more item to do. I hope you can see that on the screen. All right. So next would be the ceiling. The other thing we have to know is this room, does it have conditioned space above? Does this have conditioned space below? This could be a room that's on the 2nd floor, so I'd have no heat above. This could be a room that's over the garage. So not only would I not have heat above, I may not have heat below. This could be in addition to a house where maybe they're going to have it over a crawl space with no heat above. We need to know this. So for today's example, we're going to make believe that we do have heat below. Okay, we're going to have the heat below, and we're going to have no heat above. So what we're going to do for the ceiling is we're going to have 10 times 15. The R value of the ceiling was a 30. I want you to divide 1 by 30, and you should get a 0.033 0.033. So 0.033 is my U value, okay? And we do that math, and we get 277.2. Add all that up, I should get 5,799.36 BTU. We could call that 5,800. That would be my heat loss for that particular room. So let me stand up off to the side so you can see the board. That would be my heat loss for that particular room. And then we would figure out how much baseboard, since we're going to use baseboard for today, how much baseboard we would need. If we were going to use baseboard, it would be a 180-degree input baseboard. That would give us 580 a foot. So then I would ask you to take that 5,800 and divide it by 580. So let's do that math. Oh, come on, let's go, phone. All right. So take 5,800 and divide it by 580, and that would tell me I need 10 feet of baseboard for that room. Okay, questions?
Been answering right along. Couple, guy asked where do you get the R value from? You went through that, so he got his answer he was looking for. And other than that, we're looking good. Yeah, we're looking good.
Okay, gentlemen, we have a really cool diagnostic tool today that everybody has access to. It's called Google. So if you're never sure about what to do, you can always Google it. How do you get the R value? How do you get the U value? What should be the R value for this type of construction? Trust me, I use it all the time. All right. When in doubt, Google. And then number two, give us a ring. Call us up, email us. We're pretty good at this. We know what we're doing. Okay. All right. So if we have no more questions on this, we're going to move forward to start designing our plan. All right. So going forward, we have our floor plan in front of us. And what we did for you is we did the BTUs for the whole floor plan per room and for the whole project. But what I just did was to show you how we got those numbers. So you'd be doing this heat loss on a room by room basis, total it all up to get the total BTUs for this particular project. So as you're looking at this, our total BTUs for this project is 52,320 BTUs. Now I've got to pick a boiler. All right, so we're going to concentrate on condensing boilers today because we want to make the most efficient system as we can. And I want you to understand something. One of the reasons for doing this heat loss is so you guys know exactly what the project needs. You're not guessing. That's a big deal. That's a big deal because when you then go to sell the project to Mr. and Mrs. Homeowner, you can offer them at least a good, better, best offering. All right, we're going to do a class on how to sell comfort systems going forward. It's really a class on how to sell anything, but it's really a class on how to talk to people and find out their needs. So if we find out what the homeowner is looking for and they tell you, yes, they want an efficient system, I'm going to live in this house, for the next 10, 15 years, that's the plan. I want it to be efficient. I want to help the environment. I want to be green. Well, then you want to make sure that you can design the most efficient system. The only way to do that is to do a heat loss. Even if I was going to replace somebody's boiler, I still want to do a heat loss because, gentlemen, there's a very good chance that what was there to begin with was oversized. Because years ago, everybody went to zero, and that's what they did. And if the boiler was oversized, that means the amount of baseboard, since we're concentrating on baseboard today, was definitely oversized also. And doing the heat loss and knowing exactly how much baseboard was then installed on that particular project, that allows you then to offer the possibility of using a condensing boiler for that particular job. And you could show them how it's going to condense majority of the heating season, if not the whole heating season. And my home is a perfect example of that. My home was oversized dramatically based on the heat loss of my house, which I did 3 times. I only needed 57,000 BTUs to heat my home. And I had 130,000 BTU net boiler heating my home. And I also had 101,540, if I do recall, amount of baseboard installed in my house at 180 degrees. So knowing that I have twice the amount of baseboard that I need, I can put a condensing boiler in my house and run it at lower temperature and condense a majority of the heating season and make my house more efficient, lower my costs, and be happy. So that's the importance of doing this heat loss. Okay, so now we got to pick a boiler. So we're going to look at a boiler by NTI. We're the NTI reps. So yeah, we're biased, but that's our job. Okay. And first off, I want you to take a good look at the boiler, because look at the jacket, look at the way it presents itself. It's an appliance, and it's made to be installed in living space. That is the European model. These are made in Canada, all right? But that is the European model. So if you were in Europe and you saw this boiler in the home, it would probably be in the kitchen or maybe even in the master bathroom, because it's got an appliance look. All right, so that's one thing about it. It's got a digital screen on there for programming it and setting up the boiler in very plain, simple language. All right, so that's easy to operate. It's going to be a two-pipe system. We're going to bring in outdoor air for combustion, and then we're going to vent either through a chimney chase or through the sidewall. All right, so we can have two pipes here for combustion. Another very unique thing about this boiler is it comes with built-in Wi-Fi. And as an NTI installer, if you install this boiler, register this boiler, and register it for Wi-Fi, you can run this boiler either two ways. You can run it off of outdoor reset, which it comes with that module that you would hang outside the building, or you can run it based off of internet weather. So you can follow, the boiler will follow a weather pattern based on the internet for its local area. And since it's a condensing boiler, this boiler has the ability to be a 10-to-1 to an 11-to-1 turn down. That means I either have 10 steps or 11 steps of firing as low as needed for the job up to as high as needed as the weather changes. This is a weather reactive system. So if my boiler can change its output based on what's happening outside, I should have a much more comfortable and a much more efficient system. Okay, I hope everybody understands that. That's really important. Another really key feature about NTI boilers, these condensing boilers, is we have a boost function built in. So a lot of times we go out to the jobs and we see these boilers installed and the outdoor control is not connected to it. The wire's just hanging next to the boiler. And the reason being is the contractor replaced a cast iron boiler, put this in, set it up for outdoor reset with all the good intentions, and the homeowners used to being blasted with a lot of heat from their old system, so it doesn't feel the same. So there's two things we have to do, guys. We do have to educate them as to how the boiler is going to react. We do have to educate them that, do you feel comfortable in the room? Don't be fixated on a number on the thermostat. And if I set this boiler up with the boost function, that means that if I'm taking, I believe it's more than 10 minutes to hit my room set point, the boiler is going to boost up the water temperature automatically. And then the next cycle for heat, the next call for heat, that will be our target for what we're looking at next time. So that boost function enables the boiler to function the way it's supposed to function, and the homeowners will be comfortable. So use that to your advantage. It's a big deal. Yes, sir. We got a question.
As soon as you wrap up your boiler talk, there was a question here about the windows on your heat loss design, and does it matter direction of the windows?
No, that's a great question. And Johnny Barber put this to me very clearly, because I kind of asked that question once myself. We do the heat loss based on the average coldest day of the year, and it's definitely going to be coldest that day at night. And it's dark all the way around the house. So it really doesn't matter.
How about northwest winds and stuff like that?
Yeah, if I've got a lot of glass facing, north, and I'm going to have winds blowing against it, there's really not much we can do in that regard, other than making sure I'm talking to the builder to make sure they're going to seal that as best as possible. I can't change the size of the glass, We just have to make sure that they seal it as best as possible. And knowing how many BTUs we're going to need for the room, if we can't get it all in, since we're concentrating on baseboard today, we're going to have to look for other options to get that heat in. And we're going to discuss that today. All right. All right. So as you're looking at the NTI boiler, let's figure out what all these numbers mean. Okay. I got my people in the background giving me cues. 7:30. Pick it up, Jim. All right. I'm going. So here we're looking at the NTI boiler, and you should be able to see my pointer on the screen. So you can see heating input on that TRX 085 of 9,400 up to 85,000 BTUs. So this is a 10-to-1 or an 11-to-1 turn down based on BTUs, and this boiler can get down as low as 9,400 BTUs. I need a boiler to do 52,320. What do I pick? Well, I've also got heating capacity here at 79,000 BTUs. Then I got a net AHRI rating at 69,000 BTUs. What does that mean, and what number do I use? Well, the net AHRI rating is basically the rating that we used to call net IBR. And that means that boiler is going to be installed in unconditioned space. All right, so that means it could be in a basement that's not heated. It could be out in a garage. All right, since these boilers can really be mounted anywhere in the house, you know, let's say you even put it up in the attic space. That's unconditioned space, and that rating is telling us I'm going to lose 15% of my heat from the boilers that the boiler's producing off of the jacket and off of the near boiler piping before I get those BTUs into the home. And there used to be a time in New Jersey where houses along the shore, the boiler was literally under the house in the crawl space. So that would be exposed to the elements. So we would have to go with that rating because I'm going to lose 15% heat loss off of the jacket and off of the near boiler piping. The other rating of heat capacity means now that boiler is in conditioned space. So if my basement is heated, that means I'm not going to lose that 15% off the jacket or off the piping, and I can use that as a higher rating. So for today, we're going to use, let's say this is going to be in a basement and it's unconditioned. So we'll use the net AHRI rating at 69,000 BTUs. Since my heat loss is only 52,320, it's a perfect size. We've got it as close as we can. We're not oversized. And now the boiler is going to react to outdoor air and change its output. Can't get a better scenario than that. Any questions on that?
Yeah, one question was, are you going to use an indirect on that, or are you going to use a combi style boiler?
All right, great question. And here's what I have to say about that. Looking at your floor plan, I've got a master bath and I've got another bath. So we're going to size our domestic heating load based on shower heads. So I've got 2 shower heads in this project. This is not really a big project. A combi boiler here would be a good choice. I think it would be a good choice. One thing you have to be very aware of with combi boilers, especially in this territory, our water quality, pardon me, is not good. All right. You want to have a filter system in front of that to protect that heat exchanger from very hard water. All right. We happen to represent A.O. Smith. We have a product preserver filter that if you're doing anybody's combi in this territory, I highly recommend you put that in front of the boiler to protect the domestic side and keep that heat exchanger clean. If I was in an area where the water was really dramatic, and I'm talking about Sussex County in this territory, upstate New York, I would assume we've got some really bad areas too, as in Long Island. If it's really bad, and maybe you're even dealing with a well system with no type of filtration to take sediment out, then I would go with an indirect. At least I've got a place for all that stuff to settle at the bottom of the tank. I can't have that in the heat exchanger of a combi. We'll kill that combi way before it's time. Okay? So those are my thoughts on that. All right. One last thing. If this was a project that had more and more bathrooms, and my domestic load starts to get higher than my heating load, maybe a combi wouldn't be a good choice there. Maybe an indirect would be better because we would build up the ability to have some storage available. So if multiple showers are going to be used at once, I've got a dump load and I got recovery time built into it. We'll bring that up a little bit more as we go into this program about how to figure out recovery time. All right, we'll do that. So everybody should be feeling pretty good about that. Okay, so I've done my heat loss. I picked my boiler. Now we've got to pick our heat emitters per room. So I'm going to show you two different baseboards here. First one is called Compact. This is a very popular baseboard here in our territory. Yes, we represent it. I'm just doing my job. All right. But you have the slant fins of the world out there, the NBCs of the world out there too. And on the top, you're going to see two ratings. Every baseboard manufacturer, there we go, gives you ratings based on 4 GPM and 1 GPM, and then temperature ratings across the top of their spec sheet. So here at 4 GPM at 180 degrees, that compact board will give you 620 BTUs a foot. Impressive. But I don't want to run my combi boiler at 180 degrees. I want this boiler to condense. So go to your questions and type in, what return water temperature do we need in order to make that combi boiler condense? I'll give you a couple of seconds here to type that in, and you guys let me know.
$120, $140, $130. Gas or oil, doesn't matter. Temperature, 20 degrees, 135, 120. Okay. They're all landing in the same area.
They're all landing in the same area. Everybody's got the right idea. So if you answered 130, 120, absolutely spot on. 130 is the mark we want. If you weren't sure, that's what we want. We want the return water temperature to come back at 130 so we can cool down the flue gases and make them condense. So what does that mean here? Well, if I look at my baseboard chart, let me get my pointer here. That means if I want to maintain a 20-degree delta, that means I should be feeding 150 degrees to that baseboard. That would mean that my output drops down to 420 a foot. So if we took the foyer at 2,240 BTUs and 2,240 BTUs, and we divided that by the 620, which was 180, I'm going to need 4 feet of baseboard in there. If I divide it by 420, all right, I'll end up needing 5.5 feet. So as I lower the water temperature on standard board, I'm going to have to increase the amount of board I have because I have a lower water temperature. Now on the bottom, I've got another product here called Synergy Baseboard. This is another product made by the Mestec company. And you can see at 150 degree output at 4 GPM, this is going to be 597 a foot. That's just as good as high temp baseboard at 180. How does that baseboard operate that way? Well, what they did was they made the fins that go on the board itself, the piping, larger, and they added more fins. So the more surface area I have, the lower the lower the water temperature I feed it, I can still get higher output. And you do have products out there today that are kind of fan-assisted panel rad type of products where I could feed low temperature, blow air across those fins, and even get higher output. So there are ways to get BTUs in a room if I don't have enough wall space. So to really make this boiler sing, let's concentrate on the Synergy baseboard today. So we're going to use that water temperature of 150 at 597 per foot. So what I'd like you to do is look at your floor plan. You've got the BTUs per room. And I'd like you to take the BTUs per room and divide it by 597 and write down how much foot of baseboard you'll need per room. All right, so get your calculator, get your pen, have your floor plan in front of you. Start doing that, okay? And I'll put the first one up there. So the foyer, again, at 2,240 BTUs, we divided that by 597, and you should get 4 feet. Next room we're going to do is going to be master bath. So look at your master bath. at 1,920, divided by 597, you should all get 3 feet. Okay. Next one we're going to do is going to be the kitchen. Kitchen, 7,800 BTUs. Kitchen's going to be, I'm going to tell you this, the kitchen's going to be a challenge. I'm going to have cabinets in there. There could be islands in there. Where am I going to get this baseboard? So do your math. You should get 13 feet. So to move things along, the dining room at 4,680, 8 feet. The bathroom at 2,880, 5 feet. Bedroom 1, 6,240, should get 10 feet. Bed 2, 10 feet. Living room, 17 feet. Master bedroom, 17 feet. Any questions on how we got the footage for each room? We took the BTUs of the room and we divided it by the output of the board that we chose, which was 597 a foot. Anything, John? Any questions? All right, we're good. Excellent. All right, so now we know how many BTUs we need for the whole building per room. We've picked our boiler. We've picked the amount of heat emitters we need per room. Now let's decide, how are we going to zone this? This is interesting because I will have contractors come back to me and say, Jim, I really need to get this job. Take the zoning out. All right, take costs out of the job. Take the zoning out. Gentlemen, we're not going to do that. Stop. We're not going to do that. Zoning is comfort. You install and sell comfort systems. You have to believe that. You may be a marvelous technician. Actually, you are a marvelous technician. I know you are. But you sell and install comfort systems. Zoning is comfort. Don't skimp on zoning. It does not add tremendous cost to the job. A happy customer is going to get you more jobs. Don't skimp on the zoning. So I need you guys to go to your question box and type in how many zones. Do you want 1? Do you want 2? Do you want 3? Or do you want 4? Type it in and let's see what the how majority rules here. All right, it looks like consistency is coming through it. People are saying 4 zones.
1, 3.
Okay.
Majority is 4s.
Great.
4 zones.
Excellent. Good. You guys are thinking the way I want. A lot of times when I do this class, somebody will say, well, I'm just going to do it as 1 zone. It's not that big. There's no good place to put a thermostat. And even though you can get thermostats today with remote sensors, I could do an ecobee and have 4 remote sensors here so I can average the whole floor plan. It still is just an averaging. It's not giving the comfort that we want, especially in the bedrooms. Same thing for 2 zones. We get to 3, we're getting closer, but I do see this as 4 zones. I could put the 2 bedrooms together as a zone, that dining, living room, and bath as a zone, the foyer, master bath, and master bed as a zone, and the kitchen, I think, should stand alone because it's going to be a challenge. So if that's what we've decided, that's what we're going to do. Now, on your screen right now, you should see the kitchen with those cabinets drawn in. And we said, what did we say? We needed 13 feet of baseboard for that kitchen. Guys, where am I going to get that? Where am I going to get that wall space? There has to be a door or at least a walkway from the foyer to get in through that kitchen. There's got to be a door by the master bath. Or maybe I got the wall there. The door to the master bath is more in the master bedroom, my bad. But there's going to be a door for the master bedroom, and I'm going to have some type of open space to get from the kitchen to the dining and the living room. I don't have a lot of wall space. This is going to be a challenge. So let's see how this would look. So here we drew out the zones for you, and we color coded them, okay? So I got the bedroom 1 and bedroom 2 as a zone. That's my red zone. My blue zone is dining, bath, and living. Green zone is foyer, master bath, and master bed. And the kitchen is kind of standing on its own. And I got to figure out a way to get some heat there. You'll see that we have the baseboard elements on the outside walls. We do that because that will be the coldest part of the room. And I want to blanket that wall with warm air. So that's where we're putting our heating elements. So we do have other options for the kitchen. And let's say I can grab some wall space and use a panel radiator. You can get them today that look really cool. All right, some European designs that look really cool. Some of them can actually look like art. And you can get some other ones that look like an industrial type of product. Your choice, homeowner's choice, really, if you're going to have that as an option. Even with the panel rad there, that still may not be a comfortable room. I may want to warm that floor with some radiant tubing. I can run a combination of maybe the panel rad and some floor warming to make sure I keep the room to temperature. And when I'm near the front of that kitchen, where there's probably going to be some glass, and I got, cabinet in front of me, glass in front of me, a tile floor, no heat below, but my mechanical is under there. And if I'm standing there in bare feet, that could be for an uncomfortable floor. So we could do a combination of the panel rad and floor warming, or if the budget doesn't allow, maybe just a straight panel rad to do the heating for that room, or just a straight radiant option. All right, so any question as to why we did what we did? How, why did we zone it this way? That was my preference, but a majority of you wanted to go that way. Any questions, Sean? Anything?
Just a couple of people saying toe kick heater, different types of wall rads,
Yep.
and radiant.
Yeah, I'm a fan of radiant. I really like radiant. When I first got here at Wales Derby, we didn't have a radiant line, and we sold a pile of Beacon Morris kick space heaters, and we still move them a lot. But there's a tendency sometimes they could be noisy. I'm blowing air across the floor. Anytime we're moving air and heating, there's a chance that people may be uncomfortable. Radiant could be a nice option. Even a radiant ceiling could be a nice option if I even don't have enough floor space because there's an island in the middle and I got that taking up available floor. We can do radiant in walls and ceilings also. I also just want to point out that the way the boiler is piped as primary, secondary. And you can see we have the circulator on the supply side. We are pumping away from the boiler. Yeah, I know the expansion tank's not in there and all the other fill valves and stuff. Neat and clean, just so everybody can see what we're doing. But we do want to pump away. We do want to add positive pressure to the system, which we will go into detail going forward in our next classes. All right, so we're going to zone this the way we are. Now, how do you guys want to zone this? Do you want to zone this with pumps or do you want to zone it with zone valves? That's another thing that we're going to talk about in detail when we go into our next classes. It's a small project over here. I would do this as one single circulator and zone valves.
Zone valves are leading on that.
Zone valves are leading. Okay, fine. I know when we cross the river and go on to into the island there, they do like to lead with zoning with circulators. And, that's an option here too. But again, if you figure out the BTUs that you need, the GPM you need per zone, they're going to be so small, zoning with circulators could be kind of rough, but we could do it. So one of the things I'd like you to do is take a good look at all your loop lengths and the BTUs per zone. And I'd like you to total them up. So we know the BTUs per zone, and I'd like you to get your best guesstimation, and I'll put the screen back up there, of how long you think these loops are, because now we have to figure out, if I'm going to zone with circulators, how many GPM and feet of head per zone, or if I'm going to zone the whole project with one circulator, what's my GPM and head for the whole project? So there it is again. So if you add up the zones, add up the BTUs per zone, we'll be able to get our GPM. And how are we going to do that? John told you last week about the universal hydronics formula. To figure out GPM, we take the BTUs, we divide that by 20 degree delta T times 500, or 10,000, because that's what we're using today. It is on your page 44 of your download from last week. It's the first item you see there. It's also in your takeaways. It's the last item you see there. So to save some time, I'm going to move us along a little bit here. And if I take the red zone, and up to 2 bedrooms, that's 1,200 BTUs. And if I take 1,200 BTUs and divide that by 10,000, I should get 1.2 GPM. Let me know if somebody's saying, like, write this on the board, and we'll do that. And if I do my best guesstimation as to the length of the loop, I came up with 84 feet. Okay? We'll address the head afterwards, but I just want to say that's how I got the total equivalent length of that loop at 84 feet. The blue zone, add up all those BTUs, you should get 17,960. And if we divide that by 10,000, we should get 1.8 GPM. Okay? And if we give our best guesstimation, or, looking at the dimensions on the rooms, that blue zone total equivalent length should be about 98 feet. Let's go to the green zone. We add up the green zone of the foyer, master bath, and bed. That should be 14,560. Divide that by 10,000, you should get 1.5 GPM. And that looks to be about 103-foot loop. And then our black zone, which is going to be that panel rad there, let's put it back in. That's 7,800 BTUs, and it's about a 29-foot run. So 78,000 BTUs, divide that by 10,000, it's 0.78. So let me give you a trick. If you were scrambling with your calculator, punching all these numbers in, I'm going to give you a simple, easy trick. If I'm going to use a 20-degree delta, and I know that number is now going to be 10,000, then I'm dividing my BTUs by. Whatever your BTUs are, take the comma and move it to the left one spot. So if I've got 17,960 BTUs, if I move that comma to the left, it's going to be 1.79. So that's 1.8. If I've got 14,560 BTUs, move that comma to the left, I should get 1.45, or call it 1.5. If I've got 7,800 BTUs, move that comma to the left, it'll be 0.78. All right, and we can call that now a 0.8. That's how simple that is. If you change the delta T that you want, you may have to do some math with your calculator. But if you do a 10-degree delta, you could still do the same thing that I just did, but then just double the number. Because instead of dividing it by 10,000, you're dividing it by 5,000. All right, so that 0.78, if that was a 10-degree delta, will turn into a what? It's a 0.8 now. It's going to be a 1.6. Hope that makes sense. Anybody questioning that, John? We're good? All right. So now head. We have to figure out the head loss, because that's the next part of the equation to sizing a circulator. So in your page 44 of your TACO download from the TACO catalog, head loss, the easy method was to take the length of the longest loop, but we're going to do it individually. So take the length of that loop. I want you to multiply it by 1.5 and then multiply that number by 0.04. By multiplying it by 1.5, what we're doing is we're actually adding 50%. I'm not measuring up every single piece of pipe, counting every elbow, any T, or any pressure drop going through any valves. By adding 50%, we're adding that in there. We're adding the fudge, as we say, into that. And then multiplying it by 0.04 means I'm not going to move the water through the piping any faster than 4 feet per second. So if we did that for 84 feet, take 84, multiply that by 1.5, multiply that number by 0.04, and you should get 5 feet. Okay? 98 feet, we do the same thing, times 1.5 times 0.04, you should get 6 feet. Or it might be close to it, 5.98 or something. We're going to call it 6 feet. 103, multiply that by 1.5 times 0.04. You should get 6.18. We could call that 6 feet. And if it was 29 feet, you do the math, it should be close to 2. We'll call it 2 feet. Okay? Now I'm going to give you a trick for this too. Not that it's a trick, but it's something that's pretty simple. 100-foot run is a very common loop length. Most of the time when contractors call myself, John, or Anthony, or Rick, or Rob from our CSG group, and they're asking us, help them decide a circulator, what's your longest loop? And it starts off at about, I'm going across the house, I'm up and down, and I'm 50, 60, 70, 80, it's about 90, call it 100. It's always 100. So if we do a 100-foot loop times 1.5 times 0.04, you should get 6. So that's the magic number to know. 100 foot equals 6. Why? What if we made it a 50-foot loop? No calculator needed. It'll be 3 feet. What if we cut 50 feet in half and make it 25? No calculator needed. It's now 1.5. So if I know those 3 numbers, what if I go now to 125? Well, if 100 was 6 and 25 was 1.5, it's 7.5. 150 should be 9. 175 should be 10.5. And 200 would be 12. So I use that. I know John uses that. The other guys use it. We know what a 100-foot run is in copper. And this isn't copper. Immediately, we know it's 6 feet. Okay. So now if it's anywhere between, below 100, we can get awfully close. We can use our universal hydronics formula to see how many BTUs we need to move by looking at a rating on a boiler, or if you're telling us how many BTUs a fan coil needs, give us the length of the run. Hey, we know that that circulator is either sized right or not sized, and we can help you that way. Great troubleshooting tool for you. I hope that made sense. Anybody questioning that at all?
We just had a question about the 0.04, meaning 4 feet per second. So we're trying to move water between 2 and 4 feet per second.
Right.
And that's based on a 100-foot run.
Right.
So if you exceed that 100-foot run, you still have cushion in there. You might be a little less than the 4 feet per second, but you're still good for a hydronic system.
Yeah. Please understand, we're the TACO reps. We made circulators here that are really small and circulators that are the size of a small pony. If you want to put 100 GPM through a piece of half-inch pipe, we could do it. But they'll hear it from here to Newark. All right. We don't want to do that. That's why that 4 feet per second is safe. As you heard John say, the lowest number would be really 2 feet per second. And John will go into more detail on that when we do week 3, when it talks about getting air out of the system. All right. So moving on here. All right. Now we're going to size our circulators. So there are the numbers, and that's how we came up with them. Okay. So we've got choices today when it comes to circulators. Hey, we're the TACO guys, so we're going to use TACO as our base of operation here. And besides our standard single speed circulators that we have variable speed circulators. We've been talking about this stuff now for at least 3 or 4 years. And we have 2 types. We have delta P circulators and delta T circulators. A P pump will change its output based on amp draw changing, based on pressure against the impeller as zones open and close. A T pump will change its speed based on temperature differential. My delta T pumps come with 2 thermistors, one that would go on the supply, one that would go on the return. I can dial in a 5 to a 50-degree delta however I want, and that circulator will measure temperature and maintain whatever delta T we want. And since I'm using a condensing boiler today, I would use a circulator like that on my system side. The boiler will have its own dedicated circulator to make sure we've got proper flow across that heat exchanger based on manufacturer's recommendations, which could be a 20, a 25, or a 30-degree delta in itself. And as the boiler changes its output, my T circulator doesn't care, because all it's going to do is maintain whatever temperature differential we put in there. So if my boiler is going to change its output based on the weather conditions changing all the time, and if my circulator also did the same thing, I should have level comfort through my home at all times. Mr. and Mrs. Smith would never know things are changing. They just feel comfortable. Now I'm going to make a bad joke, because I have a cast iron boiler in my house that I added outdoor reset to, and I use a delta T circulator on it. And I have a very sensitive thermostat at home. If you guys have one of these on your finger, that is my thermostat, okay? Very sensitive. And when we put the proper boiler in and we put the outdoor reset on there and the delta T circulator, my lovely thermostat told me that, I don't know what you did, but anywhere I walk in the house, it's just comfortable. So gentlemen, I'm living with it. I know it works. Take advantage of that. Okay, but I'm going to show you two different options here because budget's always an issue too. So first option could be the Taco 0015 E3. This is a 3-speed variable speed delta P circulator. If we pick low speed, that circulator will maintain 5 feet of head all the way out to 12 GPM. And it'll vary its speed as it runs along the 5 feet of head mark as zones open and close. And if we get out to the far side of the curve, and let me get my pointer on there. If we get to the far side of the curve here, then I'm going to be running at full speed, which would be 44 watts, still half the amount of wattage that a 007 runs. And I want to point something else out to you. If I can vary my speed out to 12 GPM, we could take the universal hydronics formula, and if I can divide a BTU by 10,000 to get a GPM, I could take a GPM and multiply it by 10,000 to get a BTU. So gents, I can be varying my speed, maintaining 5 feet ahead out to 120,000 BTUs. Okay? I want you to understand that. That's what that number means. That's pretty impressive. So if we look at our project here, wow, our highest head was only 6 feet. We do have the potential to maybe set this at low and run this circulator at 5 feet of head for the whole heating season. Now you're going to say to me, well, wait a minute, Jim, we've got 2 zones that needed 6 feet ahead. And if I ran one circulator for this job, I'm picking my highest head as my mark, okay? And you said it's 6 feet, the math said it's 6 feet, but you're telling me if I set it at 5, I'll probably be okay. Well, we could discuss this many ways, but in reality, most of the heating season, we're only at 40% capacity. So there's a very good chance we could run at 5 feet of head. If not, you can bump it up to medium, and I can handle 6 feet. But what would happen is if we did bump it up to medium, so let's remember, I need 52,320, so I need 5.2. So 5 would be my mark here for GPM. At 6 feet ahead, I'd be up here. But we have this thing called a system curve, which would start down here and work its way up this way. All right, because that's the design of that particular install. That is the system curve that will happen. So if we're doing that, and I do pick it at medium, so I won't hit 5 GPM, I'll probably end up running up here, probably around 6, maybe a little over 6. So I'm going to move more GPM than needed, but I'll be up here at the 10 foot of head mark. So I will squeeze down my delta T. I won't be maintaining that 20. And as the zones open and close, what'll happen is we'll run along this 10 foot of headline as the zones open and close. Probably over pumping each time by maybe a GPM or more, but I will be squeezing down the delta T because I'll be moving the water faster than I need. So most of the time, I only need 40% capacity, and I did go for the 5 feet of head, I'll be much closer to the GPM and that 20-degree delta if I ran down there, okay? One of the neat things about the Taco 0015 E3, just in the packaging itself, is on the box, we tell you what speed, how much head, and how much basically BTUs it'll cover. So if I set it at low, it'll tell you. If I set it at medium, it will tell you. If I set it at high, it will tell you. Right on the box, okay? On this particular circulator, if you are in the high mode, then I am not in variable speed, and I end up following the pump curve, as you can see right here. All right, as zones open and close, we will follow that curve because we have to. That's the way physics work. And I'd also be running at my highest amp draw, again, 44 watts. But a great item for you here All right, great service pump to also have on the truck. So if I'm replacing a circulator for a zone system with circulators, I can dial this down and get it really nice and tight to where I have to be. Or if it's just going to be one system circulator, there's a very good chance residentially, this would be the circulator of choice. All right, next would be my Delta T, the VT2218. And you can see here, this is a kind of a different pump curve because all it is this big green area, and this circulator will work anywhere within this big green area. So here, it'll actually create pump curves based on how many zones are opening. So instead of following one system curve and riding along a fixed pump curve, I'll actually end up running where I need to be. So if all zones call and I need to be at 5.2, the closest I'm going to get is 5. And at 6 feet ahead, this is where the two plots, lines will meet right there. What will happen is it'll create this pump curve that way, and that's the way it'll run. And as zones open and close, it'll then change its speed, either picking up speed or slowing down speed to maintain that 20-degree delta. And it'll keep creating new pump curves. So now, here are my choices. I can do a P pump, which will get me close, much better than what it would normally be if it was a standard single speed, or I can nail it with a Delta P circulator. If I nail it with the Delta T circulator, I'm guaranteeing I'm going to give that homeowner the best comfort I possibly can. Okay? So, something to think about. Talk to your Taco salespeople when you see them out there. If you see us out there, talk to us about it. If you got questions, be happy to answer them. We'll go into a lot of detail on those circulators in the next coming classes. Any questions so far there, John?
No, you're doing great.
We're doing great, and we're on time. We're getting there. Don't worry. What these dots are here, I know I can be long-winded. It happens. What these dots show you where we would be plotting here as the pump would be changing its speed based on demand. So we'll actually be creating new pump curves. All right. All right, so I like to also throw things out there to make you think outside the box. You know, we make radiant manifolds. There's many companies that make radiant manifolds, and it's a distribution point. So thinking outside the box, what if I, instead of having my supply and return made out of copper, and you know, we didn't even figure the pipe sizes yet. We're going to do that more next week. But, you know, I need to deliver 5 GPM. If you look on your page 44 that we handed out to you, that 5 GPM, that's probably going to be 1-inch pipe. So then my supply and return header has to be 1-inch pipe for this system. These radiant manifolds, you can get them as 1-inch barrels or 1.25-inch barrels. Why not, if I have a tight space, use a radiant manifold as my distribution point? I have shutoff valves built into these radiant manifolds. I also have flow meters built into these radiant manifolds, so I can really balance the system. And if I wanted to zone on it, I can by adding actuators. So if your mechanical room is going to get squeezed down into a really tight package, think of something like this. And then if you wanted to, you can run now PEX pipe to your baseboard or to panel radiators. Just make sure that you're sizing the PEX pipe properly. And that's in your also page 44 handout, where we show you the pressure drop per foot of PEX pipe based on size and GPM. All right, now let's go back to that kitchen. Gonna have to pick it up here, right? I'm at 808. No, we're in good shape. We're in good shape. So in that kitchen, if I was gonna do radiance, how do I figure out the radiant? Well, first we gotta do the heat loss, and we already did that. It's 7,880 BTUs. But I need to know my BTUs per square foot, because that'll affect my water temperature that I need to put in, and it'll also affect the surface temperature of the floor. Radiant heat is wonderful heating, but if we don't do it right, we could screw it up and have a terrible system. So we want to make sure, based on whatever the material the floor is going to be finished in, whether it's tile or wood, or if it's going to be a friendly carpet and pad for that type of install, we want to make sure that we don't go over surface temperatures that could cause discomfort. So meaning, If I have a wood floor, I want to make sure my surface temperature really doesn't go above 80 degrees. That's the way I was taught from my days at Worsbo, now Uponor. That's the way we were trained, and that's kind of still what we go to market with. The RPA Association, Radiant Panel Association, will tell you 82 degree surface temperature for wood floor is okay. I get a little worried when I tell guys you can go up to 82, because if they go to 82, they go up to 85. And that could then damage the wood floor. For tile, we can go to a surface temperature of 85 degrees. If we go above that, gentlemen, your feet start to sweat, and they'll start to sweat right through your shoes. And I've experienced that. I've gone on jobs where they weren't controlled properly. People were complaining, and the moment you walked into the room, your feet started to sweat. So if I sold them a comfort system and I'm not delivering that comfort, that's a problem. So what we do is we take the BTUs and we divide it by the room square footage. So that's where you see that 7880 divided by 221. That's what those two numbers are. And it tells me I need 36 BTUs a square foot. So I'm looking at this radiant surface temperature chart. And 36 BTUs a square foot is gonna be over here. And now I don't have many options, because when I get into a grayed out area, that's telling me you're in a dangerous area. Meaning if that was wood, technically I'm over, but if it was tile, I'm still safe, all right? And you'll also see that if I'm around here and I go across at that surface temperature, it's telling me that's a 65 degree room temperature. And gentlemen, that's perfect for radiant. That's the way we were taught. That's perfect for radiant, okay? Now, some of you may be freaking out, or your homeowners may freak out because they'll say 65 is too cold. That's a number. Understand that radiant is going to heat us up to mid-chest level. Our feet will be warm. We won't feel any cold. We're not sucking BTUs out of our body that way. We'll be comfortable up to mid-chest and cooler from here. That's where you want to be, and that's the most comfort. You always notice in the wintertime that if we are changing a light fixture up at the ceiling and the heat's on, that's the hottest spot of the house because hot air rises. Well, radiant, we flip it around and it's warmer down where the people are sitting and standing. So that 65 degree room temperature wouldn't be a bad option, okay? So what do I need to know next? Now I need to know how much tubing I'm going to put in there. And you have to know how you're going to put the tubing in. So let's say this house is already up and framed, and radiant is the option you want to go with. That's what the homeowner wants to go with, and you're going to do it. I could be on top of the subfloor with a product called Quick Track, and that will raise the floor up by a ½ an inch before my finish. Now, they may not want that because now I got a little threshold walking into the kitchen. We want to keep all the floors the same height. So we can go from underneath the subfloor. And if we do that, we're going to be 8 inches on center. So you'll see right here, if we're going to be active loop length at 8 inches on center, I take the room square footage and I multiply it by 1.5. Okay, so that's where you see 221 times 1.5. That's telling me I need 331.5 feet of tubing under that floor to deliver the BTUs to that room. We're probably going to split that into 2 loops. That's where I get the 165.75. And now I got to figure that I may have some leader, some extra length of tubing to get me to that area, because maybe I'm putting the manifold in the mechanical room. You saw by my floor plan, I had the boiler kind of in the middle of the floor. Maybe that's where the mechanical room is. So maybe my manifold will be in there. So I needed extra footage on my length of tubing in order to get into the room. So we're going to say we're going to have a 10-foot leader. So that means 10 foot on the supply, 10 foot on the return. That means I'm adding an additional 20 feet to those loops. Now I got up to 185-foot loops. I need 2 of them. And now if this is going to be primary heat, here's where I may get some pushback from some of you. So if you don't agree with me, please type it in and say why. If I'm doing primary heat and I'm underneath the subfloor, I'm going to use joist track plates. I want to make sure I'm going to deliver the BTUs properly. And I want to make sure that even if somebody messes up with the insulation under the floor, because yes, you have to insulate underneath that radiant floor, no ifs, ands, or buts, even if it's over conditioned space, you must do that. So even if they mess up the insulation and leave an air gap, I'll still be able to get the BTUs into that room. I can always tweak the water temperature. So I took my total loop length, and to find out how many joist track plates I need, right over here, joist track panels, active loop length times 0.2125, I need 70 plates. All right, so far, you've done the heat loss, you know how many BTUs. By using this simple calculation, you know how much tubing you need, you know how many loops you're gonna do, all right? We haven't ran to the wholesaler yet to figure this out. We're doing it, and we know how many plates we need. Perfect, okay? We're in good shape, ready to go.
Jim, while you're on that total lengths and everything, there was a question that came across asking about cabinets and islands and things.
Yeah, so when we're under the floor, we do have to take into account cabinets and islands. If there was an island in the middle of that kitchen, we're not going to stop pulling the tubing down that bay. We're going to go underneath. So we do take that into account in our calculations. That will be unheatable space, and you guys would not put the plates under there. You'd stop the plates before, the tubing would continue on, and then we'd pick up doing plates after the fact. You'd run the tubing right to the end of the bay, so yeah, the tubing would be underneath the cabinets, all right? We would take into account the square footage of cabinets and islands and take that out of the available floor space, and then redo our calculations to see if I still can put enough BTUs into that floor to heat that room. And if I can't, I'm going to need supplemental heat. So if we looked at that kitchen and say there was an island in the middle with the cabinets, with the island, since I'm already at that critical junction of being too high a surface temperature, I probably would still need some supplemental heat in that room. Maybe I still am going to have a panel rad in there to pick up those extra BTUs when we hit design conditions. All right, moving on. So a water temperature chart like this now is going to tell me what water temperature I'm actually going to need. So I'm looking at here, 36 BTUs would be about right here. I'm going to go across and I'm going to hit this line where it says R5. If it's tile, we're going to use a 0.05 as my, as a 0.5 as my R value. And then I'm going to find that mark, go all the way down to the bottom here, and it shows at a 10-degree delta or a 20-degree delta what my water temperature would be. And if I was at 10, I'm going to be about 135, and if I was at a 20-degree delta, I'm going to be about 140 degree. So now we know what our water temperature is.
Another question about maybe just clarify on insulation and methods of insulating.
Sure,
underneath.
sure. When I use plates, there's no air gap needed. So take your insulation, push it right up against the subfloor, right up against the plates. Be aware if it's a TGI construction and you're not doing the insulation, insulators tend to use that bottom lip and just lay the insulation there. That could leave a 2 to 3 or 4 inch gap depending how deep the TGI is. We don't need an air gap with plates. Push the insulation all the way up. Now, again, the reason why I want to go with plates, and I mentioned the insulation could be an issue, if I just use suspended tubing, which we could do, the water temperature would be much higher than what we're using. We're now going to be probably in the 150s, maybe almost 160. And when I do that, I push the insulation up, but I leave a 2-inch air gap from the bottom of the subfloor to the top of the insulation. That is critical because we end up heating by convection that way. If I push the insulation all the way up, right, against the tubing in the subfloor, and now they rock underneath, it's never going to work because now I'm not creating that convection underneath, not heating the subfloor, which ends up heating the room. That's why if you tell me, hey, Jim, we're going to do radiant, it's going to be primary, and just put the tubing under the floor, no plates, I'm going to grill you to the cows come home to make sure that you're on the job. And if you're not insulating, to make sure they insulate it properly. And be aware that when you get to the end of the bay, make sure the end of the bay is covered so it's not left open because we can lose a tremendous amount of BTUs out that way. All right. I don't want to turn this into a rating class, but I just want to show you in this design that this is an option and you should have that. Oh, spray foam. Okay. Spray foam. We have to be aware of spray foam. My tubing is okay with spray foam as long as I always get this confused. Open cell, closed cell. Which one is it? Closed cell?
Well, you can either one. You get up to 340. As long as you're under 340 degrees, you have to apply it
In layers. Yeah.
In layers. Exactly.
In layers. But I'm pretty sure, I believe it might be a closed cell is what we want to use, because as it's curing, it creates a tremendous amount of heat. All right. So now they don't have to spray a lot. 1 inch would probably be fine. And then if they want to back it up with paint, that would be fine. So we could be okay, but it's probably going to be closed cells what they're going to use. All right. All right. So moving on to figure out the GPM and the head loss for this. Oh my God, look at these charts. Cardinal sin, I've got too much stuff on the screen, but it's pretty simple. A chart like this, which I'm getting out of my Uponor CDAM, to find my GPM, I'm going down to 36 BTUs here on the bottom, 8 inches on center, and I'm going to multiply that loop length by 0.00486. We do that math, and we will come up with a 0.899 or 0.9 per loop for a total GPM for that of 1.8. Now I got to figure out what the head loss is. It's PEX pipe. On your handout from page 44 to Takeo catalog, if I got to move 0.8 GPM, all right, total. Well, here's my 0.8 GPM. I'm using 1/2 inch pipe. I would multiply it by that foot. If you want to do it down here just per loop, it'd be times 0.02, okay? And what you'd come up with is 3.7. Total would be 7.4, all right? So now we know our GPM, now we know our head, and we can pick our proper circulator. One other thing to take into account, you see another chart I have on here, which is the mixing valve. I'm going to have to use a mix valve. Now, you've got condensing boilers out there where you can program in multiple temperatures. Just understand, it still can only make one temperature at a time. So for this zone, since it's one room and it's a kitchen and they're going to be cooking, right? And if they're Italians like we are, they're going to be cooking a lot. So maybe that would be okay. But if it was something more substantial, you probably want to do a mix valve on there. We do have to take into account that there's going to be a pressure drop through the mix valve. So this comes up quite often. You see the sizes of the mix valve. And this is just standard mix valve, nothing special. All right. And you see these ratings. CV is 3.3, 3.5, 3.8. What does that mean? That means that valve is rated. Let's take the 3/4. It says 3.5. That tells you that I can move 3.5 GPM through that valve, and the physical valve body itself will impart 1 PSI of pressure drop or 2.31 feet of head that I would have to add to that so I can size my circulator properly. Okay, everybody runs to a 3/4 valve. I only have to move 1.8, almost 2 GPM. Oops, sorry. 1.8 or 2 GPM. Could I do it with a 1/2 inch? Well, if I do a 1/2 inch, I'm only going to add an additional 0.85 feet ahead. Yeah, I could do that. That's nothing dramatic. If I go with the 3/4, I'm going to end up adding a 0.75. That is added to the head loss that the circulator has to overcome, and then we size the circulator properly from there. Any questions after all of that?
We are looking good.
We're looking good, and we're going to hustle. We may not finish everything today, but we'll be okay. So what I want to quickly go over here is the difference between cast iron systems and condensing. And not so much the difference is we could take a cast iron system that you see here with 3 water temps, 3 standard mix valves, and say that's only a 10 or 15-year-old system, and the homeowner wanted more efficiency. Can we make that more efficient? We can. We can add outdoor reset to that. We can do that with our Takeo controls, the PC700 with any of our expandable controls. Does he really need 3 water temperatures here on this job? Probably not. Even if it's a basement with 2 stories and I did all 3 levels, more than likely you zone it right, you're down to 2 water temperatures. And I can even add mixing valves today that have outdoor reset built into them. That's the Takeo I valve. So we can make the system even better. We can do that, okay? Over here on the condensing side, we went over, it's 2 pipe, the controls, how much better. They're piped primary, secondary, all right? We can do internet weather, but we want to make sure they condense, all right? And we can do combis and all that stuff. So here's what's really interesting. The difference between, or how you can really take advantage of the two different boilers. You can see on this chart here, that green area, that's the most days of heating. And that green area is telling you that 60% boiler capacity will be required for 49 days. 40% boiler capacity will be required at 65 days. All right. Only 3% of the time will we need full capacity. So this is why condensing boilers can be a huge advantage, because most of the time we're not going to be anywhere near full capacity, and I can have that boiler condensing, if not all the heating season, a majority of the heating season. All right, take advantage of that. By doing your heat loss up front, you established what you need, and now you have the options going forward to design the system. Cast iron is not out of the equation. If that price was too high, offer them a cast iron system instead. All right, you can still offer outdoor reset, either with the boiler where we monitor its runtime, not the temperature. And we can also, if we're going to do any type of mixing for radiant, have an outdoor temperature control built right into it with the Takeo I valve. So take advantage of that. Other things to think about: cast iron boilers last a long time. They don't need a lot of maintenance. So if that is going to be a viable option because of budget, it's a good deal, all right? But you can still make it more efficient. Condensing, well, they do have to be maintained. And that's not a problem, guys. That's an opportunity, all right? Proper maintenance, we should get 15, 20 years out of these systems, all being installed properly, vented properly. We have a class on venting coming up, so we're going to talk about that in detail. So if they're vented properly, piped properly, and maintained, you can get good service life out of them. And the maintenance is not a big deal. If you set it up right on the install, maintenance is pretty easy. It's a once a year you're getting in there, cleaning out the heat exchanger. If you got the filter in front for the combi side, that combi will be nice and clean, and you really shouldn't have any difference there. But these boilers are going to condense. We want them to condense. You guys already told me how they're going to condense by having a return water temp come back of 130, and that's a big deal. All right, so why is that condensing so important? Well, what we're doing is basically cooling down the products of combustion to flue gas temperatures by having that 130 come back. Flue gas is a gas, we can't see it. If I start to cool it down, it turns back to a vapor. If I cool it down even more, it turns back to a liquid. Inside that liquid is latent heat energy that I want to reabsorb back into the boiler. Okay, so what we're showing you here is if the boiler is in that condensing mode, I can have 970 BTUs worth of energy in that condensate that I want to recapture into that boiler. Okay, a gallon of condensate will then equal 8,080 BTUs. So here's another way to think about it. Cast iron boiler, if it's 82%, that means for every dollar I spend to heat the home, 82 cents is going into heating my home and 18 cents is going out the stack. Condensing boiler, on the other hand, at 90 or 95% efficiency in the condensing mode, means for every dollar I spend, 90 to 95 cents is heating my house, and I'm only losing 5 cents out venting. Okay, you got potential for 30% savings for some people by changing over their system to this way. All right, and the only way you would have known to do that is where we started today, by doing that heat loss. Once you know heat loss, once you've done the heat loss, you know BTUs that you really need, even on a boiler change out, now you have options, and you have more options for that homeowner. So if you're giving them a good, better, best, most of the time they may fall in the middle at better, and that could be that you're still doing cast iron, but you're still giving them outdoor reset, delta T circulators, all that kind of happy stuff, and you make more money. All right. So just to let you know, for every 1,000 BTUs, that's going to generate 1 gallon of condensate. That's an additional 8,080 BTUs that we can recapture into the system. And here the chart is showing you the colder the water that comes back to the boiler, the higher the efficiency. So we start in that mode up here, and as it gets colder and colder, the efficiency just keeps going up, up, and up. And we can attain that, gentlemen, if we started right from the beginning with a proper heat loss. That's what today's program was all about. I know it was a lot of math and a lot of me talking, but I hope it all made sense. So at this point, I always throw this out there to the group. If this is something you really want to start getting involved with and you want to use some of the programs that we use here, shoot us an email and I'd be happy to do a one-on-one, or if there's a group of you that want to do it, take you through how to use the program that we use here so you can learn how to do heat losses on your own. All right, it's a great tool. And by using the programs, and today's programs allow you to even incorporate the PDF right into the program, sketch around it so you can cut the time down to, a house in maybe, 20 minutes, 30 minutes. Doesn't take as long as it used to back in the day, where we had to take out our ruler and measure everything and then do the math. Okay. And if not, hook yourself up with a great distributor who's got a real professional heating man on staff who can help you, design these systems properly. All right. We are at the end. 1 minute over. Not bad. Didn't kill you. All right. So next week, week 3, make sure you sign up for week 3. Okay. Week 3, we will start going into root cause troubleshooting. Johnny's back here. He'll be doing the root cause troubleshooting. We'll be going over system pressure. We'll be understanding how we're using the expansion tank properly, pumping away, pipe sizing, all of that stuff. That starts week 3. Okay. John, any questions? Anything lingering?
I think we cleaned everything up. I did not respond to a lot of the questions. You were answering them as we were going, so I hope everyone understands that. But there was a lot of participation today, and it's greatly appreciated.
Awesome. We really thank you guys for tuning in with us. We have a blast doing this. So we'll see you next week for week 3 of Advanced Hydronic Training. Thank you very much.